Number system, the topic of computer applications in pharmacy. Content of this topic includes introduction, binary number system, decimal number system, octal number system, hexadecimal number systems, conversion, decimal to binary, binary to decimal, octal to binary, binary addition, binary subtraction, one's complement, and two's complement method, binary multiplication, binary division. Number systems are important to understand the design and organization of computer. Computer understands a number system. A value of each digit in a number can be determined by the digit, position in number, the base of number system, binary number system. Synonym is base 2 number system and base 2 system. Binary number system uses two digits, 0 and 1. A computer can understand only the on and off state of a switch. These two states are represented by 1 and 0. The combination of 1 and 0 form binary numbers. The base or radix in binary is 2. Binary number is called as a bit, that is, binary digit. A bit is defined as a contraction of the phrase binary digit. It is the smallest and most fundamental unit of data in computing and digital communications. 1 bit means only two digits in a value. 2 bits means two digits in a number. So total 4 possible values in binary system. 4 bits means 4 digits in a number. So total 16 possible values. Similarly, there is 8 bit that allowing 256 unique combinations or values. 8 bit is actually 1 byte. This base 2 system is the backbone of how computers process and store information. It forms the fundamental basis for how computers process and store data. The binary number system uses right to left positional notation, but in this case, each digit is multiplied by the appropriate power of 2 based on its position. Example of binary number 1 0 1 1 0 1. The best representation is with base 2 as shown here. Conversion of binary to decimal. To convert a binary number to a decimal number, start from the rightmost digit, that is least significant bit, and multiply each digit by increasing powers of 2, starting at marked 0 power. Lastly, sum all the resulting products to get the final decimal value. Decimal number system. Synonym is base 10 number system. Decimal number system uses digits 0 to 9. That means there is total 10 digits. The decimal number system is essential for daily life. providing precise measurements for money, weight, length, and time, typically using digits 0 to 9. Deci is a metric system prefix. That means 1/10. The base or radix is 10. The decimal number system uses right to left positional notation. Each digit is multiplied by the appropriate power of 10 based on its position. Example of decimal number represented with base 10. Octal number system. Synonym is base 8 number system. It uses digits 0 to 7, that is total 8 digits. The base is 8, that is 2 with power 3. Each position in an octal number represents a power of 8. It is widely used in computer programming as a compact representation of binary numbers, where each octal digit corresponds to 3 binary digits. This 3-bit mapping allows for simple conversion between octal and binary by representing each octal digit as a 3-bit group, facilitating more compact binary representation in computing. The octal number system uses right to left positional notation. Each digit is multiplied by the appropriate power of 8 based on its position. Hexadecimal number system. Synonym is base 16 number system. It uses digits 0 to 9 and A to F. That means total 16 digits, 10 digits, and 6 letters. To take A, B, C, D, E, and F as part of the number system is conventional and has no logical or deductive reason. However, these letters are indicator of decimal. A equals 10, B equals 11, C equals 12, D equals 13, E equals 14, F equals 15. The base is 16. Use in digital computers and microprocessors. This number system uses right to left positional notation. Each digit is multiplied by the appropriate power of 16 based on its position. A conversion of hexadecimal number to decimal number. Each digit is multiplied by the appropriate power of 16 based on its position. And finally, sum of all results. So, 44033 is the value for AC01 number. Summary of various number system. Number system. Its base, digits used, and example of numbers are given in this table. Decimal to binary conversion. Remainder method. To convert a decimal number to binary using the remainder method, repeatedly divide the quotient by 2 and record the remainder 0 or 1. until the quotient is 0. The binary equivalent is formed by reading the remainders in reverse order from the last, bottom, remainder to the first, top. Now let's convert 13 to binary number. 13 is repeatedly divided by 2. The digits of the remainders in reverse order from the last, bottom, remainder to the first, top. Make the binary number. So answer is 1101. Converse 43, decimal number 2, binary number. For 43, decimal number, binary number is 101011. Converts 225 decimal number to binary number. For 225 decimal number, binary number is 11100001. Converts 131 decimal number to binary number. For 131 decimal number, binary number is 10000011. Octal to binary to octal numbers conversion. Please remember octal to binary conversion table for the interconversion of number system. Convert octal 731 to binary. For this, make a table separating octal digits and place binary digits related to each octal digit. For octal number 731, binary number is 1110110001. Now convert binary 101101111 to octal number. For binary, number 1, 011011111, octal number is 557. But decimal to octal number conversion by remainder method. Decimal numbers are divided by 8 and the digits of the remainders in reverse order from the last, bottom, remainder to the first, top. Make the octal number as shown in these examples. Binary addition. The binary addition method is comparable to the standard addition of decimal integers, with the exception that it carries on a 2 value 0 and 1 instead of a 10-digit value 0 to 9. Let us see example of decimal addition. We always use carryover. If the sum of a column is more than 9, write the last digit at the bottom and carry the 1 over to the next column on the left. So the result cannot be denoted through a single digit. Because the largest single digit is 9, we need more than 1 digits in a value in decimal system. Similarly, whenever we would like to sum two binary numbers, we will have to a carryover if the product is bigger than 1, because in binary numbers, 1 is the highest number. Let us see. Binary addition with simple values. 0 plus 0 in binary is 0, 1 plus 0 is 1 and carryover is 0. So answer is 1. Now 1 plus 1. In binary number system, 1 plus 1 is 10. So the last digit 0 remains at the bottom and carry the 1 over to the next column on the left. For the next left column, 1 plus 0 is 1. So answer is 10. To perform binary addition, you only need to master 4 basic rules. These rules dictate how bits 0 and 1 interact and when you need to carry a value over to the next column. Please note binary addition table 0 plus 0 result is 0 with no carry. 0 plus 1 result is 1 and carry 0. 1 plus 0 result is 1 and carry 0. While 1 plus 1 is 10, so result is 0 and carry 1. Now 1 plus 1 result is 1 and carry 1. This occurs when there is an incoming carry from a previous column. In decimal addition, 1 plus 1 is 2. In binary addition, 1 plus 1 is 10. In decimal addition, 10 plus 1 is 11. In binary addition, 10 plus 1 is 11. Decimal addition, 11 plus 1 is 12. In binary addition, 11 plus 1 is 100. Binary equivalent numbering is given in this table. So the array of binary number is 0, 1, 10, 11, 100, 101, 110, 111 and so on. Perform binary addition 110 plus 111. Answer is 1101. Perform binary addition 10 10 10 10 plus 11 0 0 11 0 0. Answer is 1 0 1 1 1 0 1 1 0. Perform binary addition 1 0 1 1 1 1 1 0 plus 1 1 1 0 1 1 1 0. Answer is 1 1 0 1 0 1 1 0 0. Binary subtraction. There are two components in binary subtraction, 0 and 1. It's pretty similar to subtracting base 10 values. When you combine 1 plus 1 plus 1, you get 3. However, in a binary number system, the sum of 1 plus 1 equals 11. Since only 0 and 1 are involved here, we may sometimes need to subtract 0 from 1. In such cases, we use the concept of borrowing as we do in an arithmetic subtraction. Do you remember this? Binary subtraction table. When we subtract 0 from 0, we get 0. When we subtract 0 from 1, we get 1. When we subtract 1 from 1, we get 0. When we subtract 1 from 0, we get 1 with a borrow of 1. Take 1 from the following high order digit. Case 1. Binary subtraction without borrowing. Perform binary subtraction. 1, 1, 1, 1 minus 1, 1, 0. Start subtraction from most right side digits. 1 minus 0 is 1. 1 minus 1 is 0. 1 minus 1 is 0. And 1 minus 0 is 1. So, answer is 1, 0, 0, 1. Subtract the binary numbers 10 1 0 1 1 minus 1 1 0 1. Answer obtained is 1 0 0 0 0 1 0. Just subtract the binary numbers 1 1 0 0 1 0 0 minus 1 1 0 0 1 0. Start subtraction from most right side digits. 0 minus 0 is 0. Now, 0 minus 1 is not possible, and to subtract this 0, borrow 1 from the next higher order digit. The higher order digit will become 0. The borrowed place will now have 10. So, this is case 2, binary subtraction with borrowing. Now the 0 after borrowing become 10. So 10 minus 1 is 1. Next is 0 minus 0 is 0. 0 minus 0 is 0. Next is 0 minus 1. So borrowing from next higher order digit. So here 10 minus 1 is 1. Next is 0 minus 1 because upper digit 1 has given 1 to right side 0. This it becomes 0. So it borrow 1 from higher order digit. So 10 minus 1 is 1. Next is 0 minus 0 is 0. Gain to the answer for this subtraction is 1 1 0 0 1 0. You can confirm your answer by converting your binary digits to decimal numbers. Like here, your exercise in decimal number is 100 minus 50 is 50. Subtract the binary numbers 1 1 0 1 1 0 1 minus 0 0 1 1 0. 1 minus 1 is 0. Next is 0 minus 1. So borrowing from next higher order digit. So here 10 minus 1 is 1. After donating 1, this 1 becomes 0. So 0 minus 0 is 0. 1 minus 1 is 0. Next is 0 minus 1. So borrowing from next higher order digit. So here 10 minus 1 is 1. After donating 1, this one becomes 0. So 0 minus 0 is 0. And lastly, 1 minus 0 is 1. Subtract the binary numbers 1 1 0 0 0 0 1 minus 1 0 0 1 1 1 minus 1 is 0. Next is 0 minus 1. For this 0 borrow 1 from next higher digit. But the next higher digit is also 0. So let's see detailed process of borrowing by magnifying the upper value. The 0 that needs borrowings highlighted here. It borrow 1 from next higher order digit, which is also 0. Thus, this second 0 borrow 1 from next higher order digit, which is also 0. So, this third 0 borrow 1 from next higher order digit, which is also 0. So, this fourth 0 borrow 1 from next higher order digit, which is 1. So this one donate 1 to 0. Thus 1 becomes 0 and 0 becomes 10. Similarly, this 10 after donating 1 to adjacent 0, 10 become 1 and 0 becomes 10. Now, this 10 after donating 1 to adjacent 0, 10 become 1 and 0 becomes 10. Again, this 10 after donating 1 to adjacent 0, 10 become 1 and 0 becomes 10. So, after borrow, the upper value becomes 1 0 triple 1 10 1. Now start subtracting second right digits. 10 minus 1 is 1. 1 minus 0 is 1. 1 minus 0 is 1. 1 minus 1 is 0. 0 minus 0 is 0. And lastly, 1 minus 0 is 1. So answer is 100. Triple 1 0. Binary subtraction using one's complement. The number's one's complement is derived by reversing every 0 to 1 and every 1 to 0 in a binary. Here, if we want to subtract the binary numbers 11 0 11 0 minus 10 00 10, the number from which another is to be subtracted is called as minuend. The number being subtracted is called as subtrahend. Binary subtraction using one's complement. Steps with example. Subtract the binary numbers 11 0 11 0 minus 10 00 10. Step 1. Identify the minuend and subtrahend. Minuend is 11 0 11 0 and subtrahend is 10 00 10. Step 2. Find the ones complement of the subtrahend. One's complement of the subtrahend is 0 1 11 0 1. Step 3. Add the minuend and the ones complement of the subtrahend. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 0 remains at the bottom and carry the 1 over. 1 plus 0 plus 1 is 0 remains at the bottom and carry the 1 over. 1 plus 1 plus 1 is 1 remains at the bottom and carry the 1 over. 1 plus 1 plus 0 is 0 remains at the bottom and carry the 1 over. This carry over 1 is increment, not included in addition. Step 4. Add increment of step 3 to the result of step 3. So the answer obtained is 1000 is the answer using 1's complement. Or subtract the binary numbers 11, 11 minus 10, 10. The answer obtained is 101. Binary subtraction using 2's complement. Binary subtraction with 2's complement entails adding the 2's complement of the subtrahend to the minuend. 01101. 1's complement is 10010. Now add 1. 1's complement is 10011 is the 2's complement. 1's complement in binary is obtained by inverting or flipping all the bits of a binary number. 2's complement of a binary number is obtained by adding 1 to its 1's complement. Binary subtraction using 2's complement. Steps with example. Subtract the binary numbers 11011 minus 10010. Step 1. Identify the minuend and subtrahend. Minuend is 11011 and subtrahend is 10010. Step 2. Find the 2's complement of the subtrahend. 1's complement of the subtrahend is 01101. Add 1 to the 1's complement. So 2's complement is 01110. Step 3. Add the minuend and the 2's complement of the subtrahend. 0 plus 0 is 0. 1 plus 1 is 0 remains at the bottom and carry the 1 over. 1 plus 1 plus 1 is 1 remains at the bottom and carry the 1 over. 1 plus 0 plus 1 is 0 remains at the bottom and carry the 1 over. 1 plus 1 plus 1 is 1 remains at the bottom and carry the 1 over. 1 plus 1 plus 0 is 0 remains at the bottom and carry the 1 over. Step 4. Leave the carry out. Don't add in sum. Hence answer is 10100. Binary multiplication. Binary multiplication is a mathematical operation that involves multiplying two binary numbers, which are numbers composed of only 0 and 1. Binary multiplication is similar to decimal multiplication, except that the base of the number system is 2 instead of 10. Binary multiplication involves multiplying each bit of the first number by each bit of the second number and then adding the results. Binary multiplication table. When we multiply 0 with 0, we get 0. When we multiply 1 with 0, we get 0. When we multiply 1 with 1, we get 1. When we multiply 0 with 1, we get 0. Binary multiplication steps. With example, subtract the binary numbers 1101 into 100. Step 1. Aligning the multiplicand and the multiplier one below the other. Step 2. Multiply the multiplicand by each digit of multiplier starting from the rightmost digit. Step 3. Move to the next digit of the multiplier and multiply it by the multiplicand. Write the result below the multiplier after shifting it to the left by one position. Step 4. Repeat this process for each digit of the multiplier, shifting the result to the left by one more position each time. Step 5. Add all the results using binary addition rules. The final sum is the answer. So, 1101 into 100 is equal to 110100. Subtract the binary numbers 1010 into 101. Answer obtained is 110010. Binary division. Binary division is a mathematical operation that involves dividing two binary numbers, which are numbers composed of only 0 and 1. Binary division is similar to decimal division, except that the base of the number system is 2 instead of 10. Binary division table. When we divide 0 by 0, we get error. When we divide 1 by 0, we get error. When we divide 1 by 1, we get 1. When we divide 0 by 1, we get 0. Binary division steps. Step 1 is divide the bits of the dividend and record the quotient. Step 2 is multiply the divisor by the quotient and write the product. Step 3 is subtract the product from the dividend and write the difference. Step 4 is bring down the next digit and repeat. Binary division steps with example. Divide the binary numbers 10111011 divided by 101. Start by taking the first three digits of the dividend 101, which is equal to divisor. Step 1. Write 1 as the first digit of the quotient. Then we subtract the product from the first part of the dividend. and write down the remainder. Step 2. Next, we bring down the next digit of the dividend, 1. Now we have 1, which is less than the divisor, 101. So we write 0 in the quotient. Step 3. Next, we bring down the next digit of the dividend, 0. Now we have 10, which is less than the divisor, 101. So we write 0 in the quotient. Step 4. Next, we bring down the next digit of the dividend, 1. Now we have 101, which is equal to the divisor, 101. So we write 1 in the quotient and write down the remainder. Step 5. Finally, we bring down the last digit of the dividend, 1. Now we have 1, which is less than the divisor, 101. So we write 0 in the quotient and 1 as the remainder. Hence, 1011011 divided by 101 is equal to 10010, and the remainder is 1. End of the topic of the number system. Please note down the study questions